All right, this video is to help you make sense of the ray diagrams for converging and diverging lenses, so these two, and then also concave mirrors and convex mirrors. So I'm going to start with converging lenses when this is the object and it is outside or beyond 2f. Now notice, it doesn't matter if I go way back here or all the way up to 2f, the image is always between f and 2f. So here's what I'm going to do. That image and I'm going to put it into this chart here, and I'll make this chart available too. I'm only going to do the LOST for this particular one because you got to learn this on your own, but the location is between F and 2F. Okay, how about the orientation? Well, if you look at this thing, it is upside down no matter where I drag it. It's upside down, so that's inverted. Not upright, it's inverted. It's also very small, that's reduced. The last one is type. It is a real image or it is a virtual image. Okay, a real image is a real image because the light rays actually go through that point in space. This image appears here because all three of the rays actually go through this point. So this is a real image. All right, so there you have it. There is the loss, the location, the orientation, the size, and the type for when a converging lens has the object beyond 2f. Now I'm going to go back and look at the other cases. So when it's right at 2f, now you can see the image right here. It is still inverted. It is still a real image, and it appears to be the exact same size as the object. So I snip the image in there for at 2f. So here's your image and here's your object. You can fill out the loss. Now let's go back and look at in between f and 2f. Okay, so what's kind of nice is when I'm in between f and 2f over here with the object, the image is always beyond 2f. So that's kind of like the opposite. When the object is beyond 2f, the image is always trapped in here between f and 2f. Well, when the object is in between f and 2f, the image is beyond 2f. So I'm going to grab this picture and put it into my chart. So now my chart's getting smaller to fit all these new images. Here's the situation where the object is between f and 2f, and here's the image. You can fill out the lost here. Now I'm going to go look at f. All right, now f is a strange point with this. So you can see that everywhere up until now, the image has been upside down or inverted, and it's been out on the right side of the lens, and it's been real. When I get to F, something strange happens. You can't always really see it here because the image is way over here off the screen. But what happens, those light rays are actually parallel, which means they're never going to cross. That means that no image is formed. So that just means that you don't have a location, an orientation, a size, or a type because there is no image. The last situation is inside of the focal length, inside F, and when you come inside of the focal length, something strange happens. The image jumps over here, and now it's upright. It is actually behind the object, so watch this. When you're left of the focal length, the image is over there on the right. When you cross the focal length and come inside F, now the image is on the left. What makes this interesting, you see how it's the dotted lines that are crossing to produce this image? The dotted lines are where these actual light rays appear to have come from. In other words, the light rays never actually go through this image. They are off over here to the right. Because the light rays never go through this image, this is a virtual image. And you can see that it's bigger and that it's upright. I'll let you fill out the lost for all of these. These are the situations for converging lenses, and I'm just going to go back to this to show you it doesn't matter where you are inside of the focal length, the image is always in the same situation. It's always behind it, it's always magnified, and it's always virtual. Okay, so now I'm going to switch to diverging, and here's the object. Now what's really nice and simple about diverging, doesn't matter where I drag it, the image is always the same. It's always in front of the focal length. It's always upright. It's kind of hard to tell, but the light rays are all over here. They never actually go through the image. They just appear to have gone through the image right here. So this is a virtual image, and you can see very easily that it's always going to be smaller. So this is the easy one. The image is always smaller, virtual, upright, and inside the focal length. Here's my flow chart that summarizes pretty much everything you need to know about lenses, both converging lenses on the top here, that's right here, and then the diverging lenses on the bottom. And just to remind you, the diverging lens is the one I just covered. That's the super easy one because it always produces the same type of image. Next, I'm going to go over mirrors. So for mirrors, I'm just going to switch this to mirrors. This is a concave mirror. So here I have my chart set up to organize the mirrors. Now for the concave mirror, I'm going to do the same situations. And for the convex, that's the simple one. You'll see that at the end. So beyond 2f, when the object is beyond 2f, this is kind of nice because just like with lenses, the image is trapped between f and 2f. Doesn't matter where I go, it's always going to be between f and 2f. It's always upside down. It's always smaller. And because the light rays actually go through it, it is always real. So I did the first one for you. The location is between f and 2f. It's upside down, so that is inverted. It's small, so that's reduced. Light rays go through it, so that's real. Okay, next I'm going to do at 2f. Okay, so if I drag the object right to 2f, very similar to lenses again. Now the location is just at 2f, just like before. It's just on the same side as the object. Notice the size is identical. Notice it's inverted. And notice it is real. So I grabbed that image, put it in my chart here for at 2f. You can fill in the lost. Now we're going to go back and go with the object between f and 2f. Okay, so you're going to see some similarities here as well. When I bring that object in between f and 2f, notice the image is always beyond 2f, no matter where I go in here. And it's always upside down. It's always magnified, no matter where I go in here. It's always bigger, and it's always real because the light rays are still going through it. Okay. I dragged the image in here to my chart. You can do the lost for that, the LOST for that. The last two here, I'm going to go at f and inside f. Okay, so when I drag the object all the way to f, right at f, notice how the image flips again there. When I get it just exactly at f, which is really hard to do here, the light rays, you might be able to tell, are parallel. This means that no image will be formed. The chart looks the same for concave mirrors as it did for a converging lens. No image is formed. The last situation is when the object is inside the focal length, and notice the location is tricky, but it's completely flipped over to the other side. And notice the image is increased in size, and notice these light rays only appear to be crossing over here. The dotted lines are apparent light ray intersections. The light rays actually get reflected backwards, so they never travel through this point where the image is. So this is a virtual image. I've got my last image in there for concave. I am going to point something out here. I've been a little bit vague on something. When you're inside the focal length for this concave mirror, if you look back at this, the location really does vary. If you're looking at where the location is right here, it appears that it's inside the focal length on the opposite side of the mirror. If you back it up, it goes well beyond 2f over here. So I'm just going to have you write location varies. And then the same thing was true over here when your converging lens object was inside the focal length. Location varies. Okay, so that's just a small correction to the location, and it's only when you're inside the focal length on a converging lens or on a concave mirror. The last final part of this video, I'm going to talk about convex mirrors. Talk about convex mirrors, you actually have to grab the object and drag it over to the other side of the mirror. So what's nice about these, just like diverging lenses, you can see the image is very, very tiny over here. It's inside the focal length. It's reduced in size, and it is virtual because the light rays actually get bounced back over here. They only appear to have come from over here. It doesn't matter where I start from, where I drag the object, the image is always the same. It's always reduced in size, it's always inside the focal length, it's always upright, and it's always virtual. Final image for convex mirrors. Notice the location always inside F, the orientation is always upright, size is always smaller or reduced, the type is always virtual. This should look familiar because if I go back up here to my chart, diverging lenses had the exact same loss description, always inside F, always upright, always virtual, and always reduced, and always virtual. So I'm going to post these as a file on a Google slideshow for you to use, and you can save that and use this on the test. But here's the ray diagrams for both types of lenses, both types of mirrors explained. Thank you.